Well, to get us started, I thought I would backtrack and just do a recording for this lesson since this was the first one where we started the U substitution. So if you did want to go back and review this one with my voice, you could. And then, of course, we'll start with the next lesson with the next PowerPoint. And so I've reduced some of the animation also, and hopefully it'll be easier to download the PowerPoints with some of the animation removed. Take up less space on computers. So anyway, let's get on with the U substitution. And of course, every time we learn something in math, there's always like an opposite function, an inverse function. So if we learn how to multiply, we later learn how to divide, or if we learn how to add, we later learn how to subtract. So of course, if we learn the chain rule, there has to be a reverse to it. Right? So if you think about when we used to try to take the derivative of something like y equals sine of x to the third power, we would have to take the chain rule. Right? Because we know that if we want to take the derivative of the sine function, of course we'll just get the cosine function. Right? Derivative of sine gets us cosine. So if I want to take the derivative of y with respect to x, the derivative of sine is just cosine. So I'm thinking, okay, I just have cosine of x to the third. Except there's something inside the cosine function, right? If I looked at the original sine of x to the third, there was something inside the sine function. There's an x to the third power. And so the chain rule says we then have to take the derivative of the function that's contained inside there. So the global function, as you will, would be sine, and then inside of sine is the function x to the third power. So we got to take the derivative of x to the third power, and we end up with 3x squared times the cosine of x cubed. So if I want to go the opposite direction, if I want to integrate instead of take the derivative, I'm like, what's going on here? Well, I have to identify the main function, or the primary function is cosine. And this is a little bit tricky, trying to look at all of the stuff that's going on inside the integral and figure out what function is kind of like the main one or the star of the show, and it's cosine. And then I ask myself, well, what is contained within that cosine function? Well, it's x to the third power. So I will let u, my universal variable, stand for x to the third power. And then if I take the derivative of u with respect to x, I get 3x squared. Now, right now at this point, if I don't see something resembling that 3x squared in the integral, I'll know that I've not chosen my u very successfully. But I see that there is a 3x squared in the integral. So I'm thinking, okay, I've chosen very wisely. Let's multiply both sides of that equation by dx. And I learned that du is 3x squared dx. Now let's see how successful this was. I said let's let u equal x to the third power, and of course there is an x to the third power in that integral. Du will be 3x squared dx, and sure enough there is a 3x squared dx in the integral. So what am I left with? Well, there's the integral symbol, and there's a cosine. So x to the third will be substituted with u. 3x squared dx becomes u du. And I'm like, oh, I just have to integrate cosine. That's easy. When I integrate cosine, I just get sine. Now, because it's an indefinite integral, I have to remember the plus c. So if I integrate cosine of u, I get sine of u plus c. Now I have to back substitute. U was my universal variable that replaced x to the third power. So let's put x to the third power back in there. I've got sine of x to the third power plus a constant. There's my function. Okay, now this almost becomes an art rather than a science. It's kind of an art of what on earth am I going to have be my u? So with this next example, I'm like, okay, what's kind of like the big function, the primary function there? It's like, hey, I think that's square root. I think square root is kind of like the big primary function. And so what is inside that function? What is inside the square root? Well, it looks like 5x squared is inside. So I'm going to let u equal 5x squared. Take the derivative of u with respect to x. I get 10x. Sure enough, there is a 10x in that integral. Let's multiply both sides by dx. And I find that du is the substitution for 10x dx. So again, the 5x squared will become u. 10x dx will become du. And of course, I still have my integral symbol, and I still have my square root symbol. So I keep my integral symbol. I keep my square root symbol. 5x squared is replaced with u. 10x dx is replaced with du. I know how to integrate this. I'm really looking at u to the 1/2 power. So I add 1 to the exponent to get the new exponent. I have to divide by the new exponent. Remember my plus a constant. Never really want to divide by a fraction. So I multiply by the reciprocal. Finally, that universal variable u was a stand-in for my 5x squared. Now on the first example, I started by taking the derivative. And so of course when I integrated and I got back to my original, I knew I did it correctly. But in this case, I didn't start by taking a derivative, right? I just took the integral. I'm like, well, how do I know if I really have the correct answer? Well, if I want to check my answer, take the derivative. Right? If y equals 2/3 times the quantity 5x squared raised to the 3/2 power plus a constant, let's take the derivative. I know what has to happen. The 3/2 becomes a coefficient. I subtract 1 from 3/2. My new exponent is 1/2. Chain rule says peek inside, take the derivative. Well, derivative of 5x squared is 10x. Derivative of the plus constant, well, that's 0. Don't have to worry about that. And it looks like 3/2 times 2/3 will cancel out. And of course, exponent of 1/2 means square root. So sure enough, if I take the derivative, I have what I saw originally in the integral. So that answer checks out just fine. What is my function here that's like the star of the show? Well, actually, it looks like something is being raised to the 4th power. What's being raised to the 4th power? Tangent of x. So u will substitute for tangent of x. Now, if you're scratching your head saying this makes no sense at all, look at what happens if I take the derivative of tangent. The derivative of u with respect to x, well, the derivative of tangent is secant squared. Sure enough, I see a secant squared in the equation. So if u equals tangent of x, the derivative will be secant squared x. So my du will be secant squared x dx. Now let's see how well this matched up. Tangent of x is my u. Notice I did not highlight the 4, right? That's going to be u to the 4th power. Secant squared x dx is my du. So notice that 5 is still sitting there, but that's okay because that's just a constant, or I should say a coefficient, right? It's a plain old number. It's not a variable. So the integral symbol can just sit there. That 5 can just sit there. Tangent of x has been replaced by u. So instead of tangent of x being raised to the 4th power, u is being raised to the 4th power. And then secant squared x dx is replaced with du. When I integrate, add 1 to get the new exponent, divide by the new exponent. 5 divided by 5 will cancel out. I just have u to the 5th power plus a constant. And of course, u is tangent of x. So I'm really looking at tangent of x raised to the 5th power plus a constant. If I want to check this, well, let's take the derivative. Anything raised to the 5th power, it's easy to take the derivative. The 5 goes out in front as a coefficient. Subtract 1 from the exponent, so I now have an exponent of 4. Don't need to worry about the plus constant because that will disappear with the derivative. Oh, chain rule says peek inside. What was inside the thing being raised to the 5th power? Tangent. What's the derivative of tangent? Secant squared. So the derivative of tangent of x will be secant squared of x. So sure enough, it works. Right? When I took my answer and took the derivative of that answer, I got 5 times secant squared x times tangent to the 4th power x, which was what was inside the integral. Okay, let's do one last example here. Integral of 7 times e to the 7x dx. And so what is the primary function here? What is the big star of the show? It looks like it's being e raised to a power. So what is inside there? Well, the u will be 7x. If I take the derivative of u with respect to x, I just get 7. Sure enough, I see a 7 in that integral. So du will be 7 dx. 7x is my u. 7 dx is my du. I'm left with integral of e. So I've got the integral of e raised to the u power du. Easiest thing to integrate, right? Integral of e to the u is just going to be e to the u. Then I got to remember my plus a constant. Back substitution now. U becomes 7x. There's my answer. E to the 7x plus c. If I want to check my answer, take the derivative. The derivative of e to the x is just e to the x. So the derivative of 7e to the x is just e to the 7x. But then the chain rule says peek inside. Derivative of 7x is just 7. And there we go. And so this is the assignment we did last week on Wednesday. We had the worksheet. And so if you were in class last week on Wednesday, you've already completed that worksheet. If you were not in class, hopefully you were able to work on this at home. But this is just in case you wanted to relive the experience with my voiceover. Otherwise, you can just download the PowerPoint and view the slides at your own pace without my voiceover.